The next unit in the course is titled Complex Analysis, and in this unit we're essentially going to do a review of complex numbers with a few new topics thrown in at the end. Because the vast majority of this material is review and it's content that you should already know, I'm going to cover the material fairly quickly. I'm only going to slow down towards the end when we hit some topics that are likely to be new to you. So just to refresh your memory, a complex number is a number of the form x plus jy, where x and y are real numbers and j is the square root of -1. Complex numbers can be written in two common forms. One is the Cartesian form, where we write the complex number in terms of its real and imaginary parts. So x is the real part, y is the imaginary part. Re is used to denote the real part of a complex number, and Im is used to denote the imaginary part. The other way in which we can express a complex number is in polar form. And polar form can be written in one of two ways. Mathematicians maybe tend to write it more this way. Engineers tend to write it in terms of an exponential function because this is a little bit more compact. They're both equal to one another because of this relationship here at the bottom of the slide known as Euler's relation. E to the j theta is equal to cos theta plus j sine theta. So because of this we can rewrite cos theta plus j sine theta here as e to the j theta. So this is r in this particular expression is known as the magnitude of the complex number, and theta is the argument of the complex number. And we use the notation vertical bars to denote the magnitude of a complex number. So this is the magnitude of z, and args denotes the argument of a complex number. At this point, I just want to make a few comments with respect to the argument of a complex number. So the argument is not uniquely determined. The reason for this is that the expression e to the j theta is 2 pi periodic. So if I add any integer multiple of 2 pi, for example 2 pi k, where k is an integer, to theta, I get the same numerical value. Because of this, there's an infinite number of arguments that you could write down for a complex number. All of them are related to each other by additive integer multiples of 2 pi. Sometimes it's undesirable to have an infinite number of answers for something that are all correct. So for this reason we introduce what's called the principal argument. And what this is of all the infinite number of arguments that you can write for a complex number, it's the unique one which lies between minus pi and plus pi. And this interval doesn't include minus pi, and it does include plus pi. So it's a kind of an asymmetric interval. And the principal argument is denoted as arg with a capital A. So the argument of the principal argument of a complex number is always uniquely determined, at least if we ignore the uninteresting trivial case of the complex number 0. The complex number 0 is sort of special in the sense that you can choose any value, any real number for the value of the argument, and it's correct. On this slide I have a couple of figures that illustrate the geometric interpretation of the Cartesian and polar forms of complex numbers. So the figure on the left illustrates the Cartesian form. So in this case the horizontal axis corresponds to the real part of the complex number, and the vertical axis corresponds to the imaginary part. So the complex number x plus jy would be this point here. The figure on the right illustrates the polar form of the complex number. So we have some complex number z. The magnitude of the complex number, which is denoted by r in this figure, is the distance from the origin to the point z in the complex plane. And the argument of the complex number is this angle here. It's the angle between the positive real axis and the vector from the origin to z. When dealing with complex numbers, the arctan function is often very useful. In particular, it's useful in the context when we're dealing with the argument of complex numbers. The range of the arctan function is from minus pi over 2 to pi over 2, excluding both plus and minus pi over 2. And because of this, the arctan function always yields an angle which is either the first or fourth quadrant. In other words, we have the 4 quadrants in the complex plane, and the first quadrant is the quadrant where both the real and imaginary part are positive, and the fourth quadrant is this quadrant down here where the real part is positive and the imaginary part is negative. So the arctan function always gives you an angle which corresponds to either this quadrant here or this quadrant here. You can never get angles which correspond to this quadrant here, quadrant 2, or this quadrant here, quadrant 3. So you should keep this in mind when you're using the arctan to compute the argument of a complex number. It can never give you the right answer if the complex number lies in one of these two quadrants to the left here, because you know it can't give you an angle over here. But if the point lies in one of these two quadrants, quadrant 1 or quadrant 4, the argument of a complex number can be calculated very easily by just directly using the arctan function. We just take, if we want to find the argument of this complex number, 1 plus j, we just take the arctan of the imaginary part divided by the real part, which is just 1 over 1. Arctan of 1 over 1 is just 45 degrees, or pi by 4. On the other hand, if we want to find the argument of this complex number, this would be minus 1 minus j, this point here. We know that the arctan function cannot directly give us this angle that we're looking for. We're looking for this particular angle here, which goes from the real axis around to here. This angle clearly is greater than 180 degrees, or pi in radians. So the arctan function can't possibly give us the right answer. So the common mistake I sometimes see when students are trying to compute the argument of a complex number like this is they just blindly plug into the arctan formula and they say arctan of the imaginary part over the real part, which in this case is minus 1 and minus 1. So arctan of minus 1 over minus 1, which is of course the arctan of 1. But the arctan of 1 is just pi by 4, or 45 degrees. In other words, it's not the angle we want, which is this angle, but rather it's this angle here that we're actually going to get from arctan of minus 1 over minus 1. The good news is, however, that the angle that we really want, this bigger angle, is very closely related to this angle here that we get from arctan of minus 1 over minus 1. In particular, this bigger angle here is just this angle here with pi added to it. So if you take this expression that we've computed here and add pi to it, in other words, we instead compute this formula here, this gives us the argument that we really want, which is the argument of this complex number. So just be a little bit careful about this. When you're computing the argument of complex numbers and you're using the arctan function, you have to be very careful about what quadrant the complex number lies in. In some cases, you can directly apply the arctan formula, like over here. In other cases, you have to add pi to the result. When I was preparing the lecture slides, I couldn't quite make up my mind whether I wanted to include this slide or not. In the end, I decided to include it for the sake of completeness. What this slide has is a function called the arctan2 function. The arctan2 function can be used to calculate the principal argument of a complex number. I don't, however, recommend that you use this formula. If you understand how to use the arctan function to compute the argument of a complex number, this formula is completely unnecessary, because all it does is just enumerates all the possible cases of the quadrant in which a complex number can lie, and then it gives you a formula for computing the argument of a complex number for each of those cases. The formula is further complicated by the fact that it computes the principal argument, which is why sometimes you're adding pi, sometimes you're subtracting pi. But this formula is completely unnecessary as long as you understand how to correctly apply the arctan function. So if you really like to memorize things, I guess by all means you can memorize this formula, but my experience is students often misremember the formula on exams and then lose marks. So I'd recommend you just skip this slide, ignore what's on it, and use the arctan function as described earlier for computing the argument of complex numbers. As discussed earlier, there are two common representations for complex numbers. There's the Cartesian form, which is this form here, where x denotes the real part of the complex number and y is the imaginary part. And then we have the polar form, where r is the magnitude of the complex number and theta is the argument of the complex number. So to convert from polar to Cartesian form, we simply use the formulas here, which involve cos and sine. To convert from Cartesian form to polar form, we use these formulas here, which involve a square root and the arctan2 function. But again, I would recommend that you don't try to memorize the formula for the arctan2 function. All the arctan2 function is doing is intelligently applying the arctan function. And what I mean by intelligently applying the arctan function is it takes into consideration whether the complex number that you're trying to compute the argument of is in the first, second, third, or fourth quadrant. And then based on this, it either directly uses the arctan function, or it takes the arctan function result and adds pi to it to get the correct answer. So again, I recommend that you not memorize this arctan2 function, just know how to intelligently apply the arctan function to find the argument of a complex number. This slide summarizes a few key properties of complex numbers. The first property is that addition and multiplication are commutative. Commutative simply means the order of the operands doesn't matter. So in other words, if I have addition, I can add z1 plus z2, or I can reverse the order of the operands and I can add z2 plus z1 and I get the same answer. Similarly, multiplication is commutative as well. We like when things are commutative because we don't have to care about the order that we do things in. Complex numbers, addition and multiplication is also associative. This means it doesn't matter how you group operations. So if I have three complex numbers that are added together, z1 plus z2 plus z3, it doesn't matter whether I add the first two numbers first and then add the third number, or whether I add the last two numbers first and then add the first number to that. And similarly with multiplication. Multiplication also, it doesn't matter how you group multiplication operations. And then lastly, we have the distributive property. The distributive property says that addition can be multiplication can be distributed across addition. So if I have something like this, I have two numbers added together multiplied by z1, I can distribute this multiplication across the addition operation to get the result on the right hand side. One basic operation that we can apply to complex numbers is the conjugation operation. So if I have a complex number z that's expressed in Cartesian form, so x here denotes the real part of z and y denotes the imaginary part of z, then the conjugate of z, which we denote as z star, so a superscript star means conjugation. Z star is defined to be this quantity here, x minus jy. So you can see the only thing that conjugation does is it flips the sign of the imaginary part of the complex number. Z has an imaginary part which is equal to plus y. Z conjugate has an imaginary part which is equal to minus y. And the geometric interpretation of conjugation is shown in the figure at the bottom of the slide here. So if you have a complex number z, which lies somewhere in the first quadrant in this example, the conjugate of z is going to lie down here. And essentially the conjugate is just mirroring this point through the real axis. This is the geometric interpretation of the conjugate. When working with complex numbers, the conjugation operation frequently arises. For this reason, it's important to know some of the key properties of conjugation, and this is what this particular slide summarizes. So if we walk through each of these properties in order, the first property on the slide essentially says that taking the conjugate of a complex number doesn't change its magnitude. If I take the magnitude of z or I take the magnitude of z conjugate, it makes no difference, they're equal. The second property says that taking the conjugate of a complex number flips the sign of its argument. The third property, if I multiply any complex number by its conjugate, I get the magnitude of that number squared. And then we have a couple properties which relate to the real and imaginary parts of complex numbers, which are sometimes useful as well. And then these last three properties, we essentially have that conjugation operations can be exchanged with a number of other operations. So the first property here essentially says that the conjugate of the sum is the sum of the conjugates, and the second property, the product, or the conjugate of the product, is the product of the conjugates, and then the last property is essentially saying that the conjugate of a quotient is the quotient of the conjugates. Basically, these are just saying you can sort of interchange these various operations with conjugation. And all the properties on this slide are quite important to know, because we use them frequently when we're manipulating expressions that involve conjugation. Often we have the need to add complex numbers. The particular manner in which we perform addition of complex numbers depends on the particular form in which the complex number is expressed. If a complex number is expressed in Cartesian form, it's very easy to add two complex numbers. If we have complex numbers z1 and z2, which are x1 plus jy1 and x2 plus jy2, we can add them simply by adding their corresponding real and imaginary parts. If the complex number is expressed in polar form, effectively the way we add the complex numbers is we first convert them into Cartesian form using the formulas that were introduced earlier, and then we add the complex numbers expressed in Cartesian form. So if the takeaway from this slide really is that when you're adding complex numbers, it's very much preferred to have them expressed in Cartesian form. Otherwise, if they're in polar form, you have to first convert them to Cartesian form and then add them. So it's more work to add complex numbers expressed in polar form than to add complex numbers expressed in Cartesian form. Another basic arithmetic operation that we need to be able to apply to complex numbers is multiplication. In order to multiply two complex numbers, the approach we take will depend on whether the complex number is expressed in Cartesian form or polar form. If it's expressed in Cartesian form, for example, of the form of z1 and z2 as shown here, the way we multiply them is we simply do standard multiplication using distributive law and take into account the fact that when we square j, which is the square root of minus 1, by definition we get minus 1. On the other hand, if the complex number is expressed in polar form, for example in the form of what's shown here for z1 and z2, the way we multiply the complex numbers is we simply multiply the magnitudes of the two complex numbers to get the magnitude of the result, and we add the arguments of the complex numbers to get the argument of the result. So the takeaway really from this slide is if we're multiplying complex numbers, we prefer to have them expressed in polar form rather than Cartesian form. Yet another basic arithmetic operation that we need to be able to apply to complex numbers is division. And the approach that we take to division depends on whether or not the complex numbers involved are expressed in Cartesian form or in polar form. If the complex numbers are expressed in Cartesian form, like what we have here for z1 and z2, the way that we divide them is we play the trick of taking the quotient that we're trying to compute, z1 over z2, and we multiply it by 1, but not any version of 1, specifically 1 which is represented as z2 conjugate over z2 conjugate. So since we're effectively multiplying by 1, this doesn't change anything, but the way this helps us is if you remember, if you multiply any complex number by its conjugate, you get the magnitude of that number squared. So now what we have in the denominator here is the multiplication or product of z2 with its conjugate. So this gives us magnitude of z2 squared. So effectively what we've done is we've turned this problem of dividing one complex number by another complex number into the problem of dividing a complex number by a real number, because now the denominator is real. And then this becomes a very easy exercise to do at this point. In the case that the complex numbers involved are represented in polar form, if so for example z1 and z2 that we want to take the quotient of are represented in the form of this right hand side and this right hand side here, all we do is for the result, the quotient that we're trying to compute, the result has a magnitude which is just the quotient of the individual magnitudes, so r1 over r2, and then the argument of the result is just the difference between the arguments, in particular the argument of the complex number in the numerator minus the argument of the complex number in the denominator. And the takeaway from this slide essentially is if you're doing division, it's much preferable to have complex numbers expressed in polar form, because it's much easier to do a computation like what's shown here than what's shown at the top of the slide. When working with complex numbers, often we have to be able to manipulate expressions that involve either magnitudes or arguments of complex numbers. For this reason, it's important to know some of the key properties of magnitudes and arguments. And this is what's summarized on this slide. So if you have two complex numbers, z1 and z2, we have the following properties that hold. The first property essentially says that the product of the magnitude is the magnitude of the products. The second property essentially says that the quotient of a magnitude is the magnitude of the quotients. As long as you're not dividing by 0, we can't have that z2 is equal to 0. The argument of a product is the sum of the individual arguments, and the argument of a quotient is the difference between the individual arguments. In particular, we're subtracting the argument of the denominator from the argument of the numerator. And again, we're assuming that z2 is not 0 because you're not allowed to divide by 0. And essentially these properties all follow quite trivially from the polar representation of complex numbers. Two particularly important properties of complex numbers are given by what is known as Euler's relation and de Moivre's theorem. So Euler's relation is this relationship here. Essentially what it says is cos theta plus j sine theta can be expressed directly in terms of an exponential function, and this is true for all real theta. And we can take this equation here and we can effectively rearrange and solve in terms of cos, which gives us this relationship here, and solve in terms of sine, which gives us this relationship here. These three relationships here are all extremely important and used very, very frequently. De Moivre's theorem simply is a relationship involving exponentiation of complex numbers by an integer power. So if I have some complex number, e to the j theta, basically a complex number in polar form where the magnitude is 1. If I'm raising this to the nth power where n is an integer, I can rewrite this as how it's shown on the left hand side. I can effectively multiply this n into the exponents. This only holds for integer n, it doesn't necessarily hold for real n. However, so you need to be a little bit careful about that. When working with complex numbers, we often have the need to compute the nth root of a complex number. Every complex number has n distinct nth roots. So if we have a complex number expressed in polar form, this complex number z, where r is the magnitude and theta is the argument of z, the formula for the nth roots of z is given by this expression here. So the magnitude of all the nth roots are the same. They're all just the nth root of r. And then the arguments are given by theta plus 2 pi k over n for k going from 0 to n minus 1. And this will always give you n distinct values. For example, if we consider the square root of 1, 1 has two square roots, plus 1 and minus 1. Clearly these are distinct numbers, and if you square either one of them you get 1. But this holds in general. Every complex number has n distinct nth roots. I'm sure that everyone watching this video is quite well acquainted with the quadratic formula. If we have a quadratic equation of this form here, where a, b, and c are complex constants, it allows us to find, the quadratic formula allows us to find the roots of this equation, in other words the solutions to this equation, and in particular the solutions are given by this formula here. In the context of this course, typically what we use the quadratic formula for is factoring quadratic polynomials. So we'll have a polynomial of this form here, basically quadratic, az squared plus bz plus c, and we want to factor this into two linear factors. And the way we can do this is using the quadratic formula. We can always factor this into these two factors here, z minus z0, z minus z1, where these values are given by the roots that you obtain from the quadratic formula. So again, the quadratic formula is quite useful for factoring quadratic polynomials. On this slide, I need to introduce some terminology that relates to functions. So first of all, a complex function is simply a function that maps complex numbers to complex numbers. So an example of a complex function would be this function capital F here, where z is a complex variable. So it takes a complex variable in, z, and it gives you back this complex number z squared plus 2z plus 1. So this is a simple example of a complex function. A complex polynomial function is a mapping of this form here, where the constants a0, a1, a2, and so on up to an, and z, this variable, are all complex. So essentially it's just a polynomial function that's complex. And then we have a complex rational function. A rational function is a function of this form here. So we have a polynomial in the numerator, and we have a polynomial in the denominator. So effectively a rational function is just a ratio of two polynomial functions. And observe that a polynomial is just a special case of a rational function, because we can always choose this denominator polynomial here to be equal to 1, right? Because 1 is a polynomial. That's not a very interesting polynomial, but it is a polynomial nevertheless. And if we choose the denominator to be 1, then simply what we have is a polynomial divided by 1, which is just a polynomial. In this course, it turns out that polynomial functions and rational functions are extremely important, and we'll see later on why this is so. Next, I need to introduce the notion of the continuity of a function. So as a matter of terminology, a function f is said to be continuous at a point z0 if this limit on the right-hand side of this equation is well defined. And essentially what this is saying, keep in mind that z is a complex valued variable, and therefore z0 is some point in the complex plane. What this limit is saying is if no matter how you approach the point z0, in other words, z can get closer and closer to z0 along any path in the complex plane, as long as you conclude the value of the function f approaching along any path is the same, then we say this limit exists and it has, this particular value. As a matter of terminology, a function that's continuous at every point in its domain is said to be continuous. From a practical point of view, in this course, again, polynomial functions and rational functions are extremely important, and we can make some fairly strong comments about continuity of polynomial and rational functions. In particular, polynomial functions are continuous everywhere, so in some sense they're very nicely behaved, they're always continuous. Rational functions are continuous everywhere except at the points where the denominator polynomial becomes 0. Remember, a rational function is a ratio of polynomials, so you're dividing one polynomial by another polynomial. Because you're doing division, there's always the possibility that you could divide by 0. So as long as you're not dividing by 0, the rational function will be continuous at those points. It only becomes not continuous at places where you're dividing by 0. Next, I need to talk about the notion of differentiability of functions. So a function f is said to be differentiable at a point z equal to z0 if this limit exists. And this is just your standard, calculus that you would have learned in a calculus course before taking this one. So there's not really anything too new here. As a matter of terminology, a function is said to be differentiable if it's differentiable at every point in its domain. Here is a bunch of properties of derivatives that are listed. There's not really anything that you wouldn't already have learned in basic calculus course, although maybe the notation that's used here might be kind of confusing, but I'm sure that this is stuff that you would have already been exposed to previously. In terms of practical considerations, in this course we're very much interested in polynomial functions and rational functions. So polynomial functions are very nice with respect to differentiability in the sense that they're differentiable everywhere. Rational functions are also relatively well behaved. They're differentiable almost everywhere. The only places where they're not differentiable is at places where the denominator polynomial becomes 0. Again, remember, a rational function is a ratio of polynomials, so because you're dividing, there's always a possibility you could divide by 0. So as long as the rational function is not being evaluated at a place where you're dividing by 0, the rational function will be differentiable at that point. At this point, I need to introduce the notion of an open disk. So this particular term is only necessary for the purposes of defining analytic functions, which come on subsequent slides. In this sense, the definition of an open disk in and of itself is not so important. The more important thing is the notion of analyticity, which I'll be talking about shortly. But I need to define an open disk in order to be able to define an analytic function and so on. So this is the reason why this definition is being introduced. An open disk in the complex plane with the center z0 and radius r is just a set which is satisfying this particular relationship here. So in terms of a picture, you have some point z0 in the complex plane, and then the open disk about that point with radius r are all the points that fall inside this circle. So the shaded region up to the but not including the border. So I've drawn the border of the circle with a dashed line to indicate that the points on the border, like on the actual circle itself, are not included. And this is the fact that the border is not included is due to the fact that this is a strict inequality. It's strictly less than, it's not less than or equal. So this is what we call an open disk. Having introduced the notion of an open disk, I can now introduce the notion of the analyticity of a function. So as a matter of terminology, a function is said to be analytic at a point z0 if it's differentiable at every point in an open disk about z0. Now this condition is a stronger condition than differentiability. If we say that a function is differentiable at a point z0, all that this guarantees is at the point z0, the derivative of that function exists. But if we say that the function is analytic at the point z0, not only does this guarantee that the derivative of the function exists at the point z0, but it also guarantees that in a small circular region, in other words an open disk, about z0, the derivative exists everywhere inside that small circular region. So it's a stronger condition than being just differentiable. As a matter of terminology, a function is said to be analytic if it's analytic at every point in its domain. In other words, it's analytic everywhere where it's defined. In terms of polynomial and rational functions, which again are really important in this course, polynomial functions are analytic everywhere. This is because they're continuous and differentiable everywhere, so by definition they'll also be analytic everywhere. A rational function is analytic everywhere except at the points where the denominator polynomial becomes 0. Again, remember, a rational function is the ratio of two polynomials, so fundamentally you're doing division when you're computing a rational function, and because you're doing division you may divide by 0. So in places where you're not dividing by 0, a rational function is guaranteed to be analytic. In other places where you are dividing by 0, it fails to be analytic. At this point, I'd like to consider a couple of examples. The first one I'd like to consider is example 8.10. In this example, we're given the complex function f, which is defined by this equation here, and we're asked to determine where this function is analytic. So the first observation we can make is the function f is a polynomial function because z squared is a polynomial. And then because the function is a polynomial function, we recall that polynomial functions are analytic everywhere. Therefore, the conclusion we draw is f is analytic everywhere. Next, I'd like to consider example 8.11. In this example, we're given the complex function f, which is defined by this equation here, f of z is equal to 1 over z, and we're asked to determine where this function is analytic. So the first observation we can make is that 1 over z, this expression here, corresponds to a rational function because we have a polynomial 1 divided by another polynomial z. So this is a rational function. Because it's a rational function, we know that the function will be continuous, differentiable, and analytic everywhere except at the points where the denominator polynomial becomes 0. And you can see here, since the denominator of this function is z, this function is going to be dividing by 0 when z is equal to 0. So this function will be analytic, differentiable, and continuous everywhere except for z equal to 0. At this point, I need to introduce the notion of zeros and singularities of functions. So I'll start out with the notion of a zero. So if we have a function f and it's 0 at the point z0, in other words, if we evaluate the function f at the point z0, the result we get is 0, then we say f has a 0 at z0. So the zeros of a function are simply the places where the function is equal to 0. It's nothing more than that. Now, if in addition to a function being 0 at a particular point, so if we take our function f and we evaluate it at z0, we get the value 0. So by definition, this means the function f has a 0 at z0. But if in addition to this condition, we have that the first n-1 derivatives of this function, so this notation here, these bracketed quantities are denoting derivatives. So this is the first order derivative, this is the n-1th order derivative. So if the first derivative evaluated at z0 and then the second derivative, third derivative, and so on up to the n-1th derivative all evaluated at this point z0 are equal to 0, then we say that the function has an nth order 0 at the point z0. So this is a stronger condition. It's saying not only is the function itself equal to 0, but some of its higher order derivatives are also equal to 0 at the point z0. So this is the notion of zeros. Then if we move on to singularities, the singularity is simply a point at which a function fails to be analytic. It's the places where the function isn't analytic. In terms of polynomials and rational functions, which are the types of functions of most interest in this course, polynomial functions don't have singularities. The reason for this is we know from earlier polynomials are analytic everywhere. Because a singularity is a place where a function fails to be analytic, and polynomials never fail to be analytic because they're analytic everywhere, polynomials by definition can't have singularities. On the other hand, rational functions, we know that they can fail to be analytic at places because rational functions fail to be analytic at any point where the denominator polynomial associated with the rational function becomes 0. And in the case of rational functions, it turns out the only type of singularity that it can have is what's called a pole. It turns out that there's many different types of singularities, but the only one of interest to us in this course is what's called a pole. And now I need to introduce a kind of a formal definition of an nth order pole. So if I have a function f and I want to check to see whether it has an nth order pole at the point z0, what I do is I take the reciprocal of this function, so like 1 over f of z, and I check to see if this reciprocated function, the reciprocal function, has an nth order 0 at z0 using the definition of nth order 0 from above. And if it does, then we say that the original function f has an nth order pole at z0. Notice that when we take the reciprocal of a rational function, because we're talking about rational functions here, when you take the reciprocal of a rational function, all you're doing is you're swapping the numerator and denominator, right? If you take the reciprocal of a fraction, you're basically flipping it upside down. Just the last little bit of terminology I need to introduce for this slide. When we talk about the pole being of first order, instead we can say the pole is simple. So simple is just a synonym for first order. If a pole has order greater than 1, in other words it's 2 or greater, we refer to it as a repeated pole. So repeated is just a synonym for order greater than 1. And we can apply a similar terminology to 0. So we can talk about a simple 0. This is just a fancy way of saying it's a first order 0. Or a repeated 0, which is just a fancy way of saying it's a 0 whose order is greater than 1. For reasons that we'll see much later in the course, it turns out that we're often very much interested in the zeros and poles of rational functions. So this being the case, it begs the question, how do we determine the poles and zeros of a rational function? Well, it turns out the answer lies in factorization. So if we're given a rational function f, which is a ratio of polynomials by definition, we can always express that function f in factored form like what's shown here. And in particular, what we've done is we've factored the numerator polynomial into all linear factors. All the factors are of the form z minus a constant, so they're all linear. And we do a similar thing to the denominator. We factor the denominator polynomial into all linear factors. And we also cancel any common factors between the numerator and denominator. So if there was a factor in the numerator that matched the factor in the denominator, we would cancel it. So this is assuming everything is written in most reduced form. This is the reason why it says that the word distinct appears here. All of these constants are assumed to be distinct, meaning this kind of implies that you've canceled any common factors between the numerator and denominator. And then the A1, A2, and so on up to AM, and B1, B2, and so on up to Bn, these are complex constants. K is also a complex constant. And then these alpha 1, alpha 2 up to alpha m, and beta 1, beta 2, and so on up to beta n, these are all strictly positive integers. So they're basically how many times each linear factor is repeated in either the numerator or denominator. So once we write a rational function in this form, it turns out we can trivially read off the poles and zeros in their orders. In particular, it turns out that the constants a1, a2, and so on up to an are the zeros of the function, which is sort of makes sense, right? Because if you plug in any one of these values into this numerator, the numerator will go to 0. For example, if we let z equal to a1, then this first factor will be a1 minus a1. It goes to 0, and then the whole denominator is 0, and then the whole function is 0. So it sort of makes sense that these values a1, a2, and so on are the zeros of the function. It turns out the significance of the functions or the constants b1, b2, and so on up to bn, they're the poles of the function, which sort of makes sense because we know for rational functions the places where you have poles, in other words places where you have singularities, are where you're dividing by 0. So if you plug in any one of these values for z, b1, b2, and so on up to bn, the denominator goes to 0, you're dividing by 0, and you're going to have a singularity. So again, the b1, b2, and so on up to bn are the poles of the function. And then the significance of these other constants, alpha 1 and alpha 2 up to alpha m, these are the orders of the zeros. So the 0 at a1 is of order alpha 1. The 0 at a2 is of order alpha 2, and so on up to the mth 0 at am, which has order alpha m. And then correspondingly in the denominator you have a similar pattern. So the pole at b1 has order beta 1, the pole at b2 has order beta 2, and so on up to the pole at bn, which has order beta n. And when we're plotting poles and zeros in the complex plane, as we often will do, we often use the symbol 0, like an O, to represent a 0, probably because the O kind of looks like a 0, and X's to denote poles, probably because from tic-tac-toe we have X's and O's, so if we're using O, then we have to use X for the other thing. Anyway, so X's are denoting poles. At this point, I'd like to consider the example 8.12. In this example, we're given a rational function f. It's a rational function because if we multiply out the numerator and multiply out the denominator, we're going to get two polynomials. So we have a polynomial divided by a polynomial. And in this example, we're asked to find and plot the poles and zeros of the function. So again, the way that we do this is we factorize the numerator and denominator, factoring into linear factors, and then from this factorization we can read off the poles and zeros. So fortunately this this function is already partially factored for us, so there's just a few quadratic factors that we have to further factor. So we're going to have to factor this z squared plus 1 factor, this z squared plus 3z plus 2 factor, and this z squared plus 2z plus 2 factor. So fortunately they're quadratic, so in the worst case, if we can't factor them just by inspection, we can always fall back on using the quadratic formula. So if we focus first on the factor z squared plus 3z plus 2, so this is the factor in the denominator, you might be able to see that you can factor this just by hand. By inspection, this factors into z plus 2z plus 1. Sometimes when the numbers are nice, you can just by inspection factor it. But if all else fails, you can plug into the quadratic formula, which is what's shown here, and solve for the roots of this particular polynomial, or I should say quadratic to be more specific. And it turns out that the roots you get are minus 1 and minus 2, which are just the negatives of these two constants here. So one way or another, you end up with the factorization for this denominator factor here, z plus 2z plus 1. Then we move on to the next factor that we want to consider, which is the factor z squared plus 2z plus 2. So in other words, this factor here. In this particular case, probably it's difficult to factor by inspection because the roots of this polynomial are not particularly nice. So we plug into the quadratic formula, and what we end up with is a pair of complex conjugate roots. So we have minus 1 plus or minus j, the two roots here. So this particular quadratic here will factor into these two linear factors. This is just coming from z minus each of these constants here. And then lastly, we have this quadratic factor in the numerator that we need to factor, z squared plus 1. So the easiest way to do this, although we could use the quadratic formula, the easier way to do this is simply observe that z squared plus 1 is a sum of squares. So a sum of squares, just generally, if you have something that looks like a squared plus b squared, this factors into, it's kind of similar pattern to difference of squares. The only difference compared to if there was a minus sign here versus a plus sign here, if a minus sign for difference of squares, there wouldn't be any j's over here on the right hand side. For a sum of squares, it follows a similar pattern as difference of squares, except you throw in a j here and a j here. Anyway, so one way or another we can factor this. Probably again the easiest way is by sum of squares into z plus jz minus j. So now we've factored each of the quadratic factors appearing in this rational function expression here, so we can replace all of those factorizations with the factorizations we've computed. So this is what's been done here. And then from this we can read off the poles and zeros of the function and their orders as well. I've just rewritten this expression here over to the side, explicitly indicating the orders of all the poles and zeros. In other words, in places where some of these factors are raised to the power 1, and normally we don't write a power of 1. Just to be very explicit, I've written the powers of 1 in here, so a bunch of these factors are raised to the first power. So if you remember the way that we determine what the zeros are, we read off the constants that are subtracted from z in each of the factors. So here this is basically z minus 0 in brackets, all raised to the second power. So this is going to correspond to a second order 0 at 0. So this is where this thing here is coming from. We have a second order 0 at 0. Here we have to read this as with a minus sign, so it's z minus minus j. So this is going to correspond to a 0 at minus j. So that's this thing here. It's first order because the exponent here is a 1. This next factor here is going to give us a 0 at j, because you have z minus, and then the thing we're subtracting is the value of the 0. And it's a first order 0, so over here we have a first order 0 at plus j. Then the last factor in the numerator we have, this is going to give us a 0 at 1, coming from the fact we're subtracting 1 here. It's first order because the exponent here is a 1, so we get a first order 0 at 1. Then if we go over to the denominator, now we can figure out the poles of the function and their orders. So the first factor here, we have z plus 1 squared. So again, we have to read this with a minus sign. So it's z minus minus 1, so the pole is at minus 1. And it's second order because of the power here being 2. So we have a second order pole at minus 1. So that comes from this factor. Then if we go on to the next factor, we have z plus 2. So we read this as z minus minus 2. So we have a pole at minus 2, which is this one here. It's first order because the exponent here is a 1, so we have a first order pole. Then if we move on to the next factor, we have z plus 1 minus j. So again, we have to read this with a minus sign, so it's z minus, and then all in brackets we have minus 1 plus j. So this gives us a pole at minus 1 plus j. which is this one here. It's first order because the exponent here is a 1, so this is first order. And then if we go on to the last factor here we have z plus 1 plus j. So again, we have to read this as z minus something. So it's z minus, and then in brackets, minus 1 minus j. So this is going to give us a pole at minus 1 minus j. Because the exponent here is a 1, this is going to be a first order pole, hence first order. And basically that's all our poles and zeros in their orders. So again, it's very easy to determine this once we have the rational function written in fully factored form. And then in the last part of the example, we're asked to actually plot the poles and zeros. So this is the last part. I'll just scroll this example up so you can see the plot. Here we've plotted the poles and zeros. The things in brackets here are indicating the orders. So the poles are, for example, we have a 0 at the origin, a 0 at 0. This is this one here. It's second order, so this 2 here is denoting that this 0 at the origin is second order. And similarly for the other points. Basically the bracketed quantity is indicating the order, and then the x's are indicating poles, and o's are representing zeros.